Welcome to Tech with Koushik. This is set 4 of our AI-200 Microsoft Certified Azure AI Cloud Developer Associate Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam-ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link is in the description. Let us begin set 4. Question number 121. This one tests your understanding of container apps revisions. Background. AdventureWorks is preparing a new fraud model service revision. Current environment. The existing container apps revision currently receives all production traffic. Business requirements. The new version must be validated against a small percentage of live requests before wider rollout. Technical requirements. Both revisions should remain active during the validation period. Which mechanism should be used? Compare the options. Choice A. Enable multiple revision mode and assign a small traffic weight to the new revision. Choice B. Replace the existing revision immediately with the new version. Choice C. Validate only on a developer workstation. Choice D. Disable monitoring while changing versions. The option that satisfies the complete requirement is option A. Enable multiple revision mode and assign a small traffic weight to the new revision. This option satisfies the complete requirement because Container App's multiple revision mode allows several revisions to remain active and supports percentage-based traffic weights, which is directly suited to canary validation and gradual rollout. B. Immediate replacement provides no live canary period. C. Local-only testing does not validate production traffic behavior. D. Monitoring should remain enabled during rollout. Remember this decision rule. Use multiple revisions plus traffic weights when a new Container Apps version must receive only a controlled percentage of live requests. Question number 122. Find the decisive clue before choosing. Background. AdventureWorks operates a GPU inference workload. Current environment. Different GPU node pools expose specific hardware SKUs. Business requirements. Pods must be scheduled only onto nodes that satisfy explicit hardware placement rules. Technical requirements. The team needs direct Kubernetes scheduling controls such as node affinity in the pod specification. Which hosting platform best supports this requirement? Compare the options by fit, not by familiarity. Next, option A, Azure Kubernetes Service. Next, option B, Azure Container Apps because it exposes unrestricted Kubernetes scheduling APIs. Next, option C, Azure Functions Consumption. Next, option D, the requirement does not affect hosting choice. The best answer is option A, Azure Kubernetes Service. The decisive reason is AKS exposes Kubernetes pod specifications and scheduling controls such as node affinity, allowing workloads to target nodes that match required GPU or hardware labels. Now eliminate the distractors. B. Container Apps abstracts the underlying Kubernetes scheduler and does not expose unrestricted pod scheduling configuration. C. Functions consumption does not provide Kubernetes node scheduling. D. Fine-grained scheduling requirements directly affect the required orchestration platform. Watch for this clue in similar questions. Use AKS when placement rules depend on Kubernetes native scheduling features such as affinity, taints, tolerations, or node selectors. Approach question number 123 by checking every constraint. This is a medium question, so check each requirement. Background. AdventureWorks runs a pre-processing worker in Azure Container Apps. Current environment. Incoming work is placed on an Azure Service Bus queue. Business requirements. The worker should scale according to queue backlog rather than HTTP concurrency. Technical requirements. Replica count must react automatically to the service bus signal. Which underlying capability enables this behavior? Eliminate every option that violates even one requirement. Consider option A, Container Apps Kata-based custom scaling with an Azure Service Bus scaler. Consider option B, HTTP scaling only. Consider option C, a manually executed automation runbook. Consider option D, moving the entire platform to AKS because Container Apps cannot use non-HTTP signals. After elimination, select option A, Container Apps Kata-based custom scaling with an Azure Service Bus scaler. The requirement to solution match is container apps custom scaling uses Kata to evaluate external event sources. The service bus scaler can monitor queue backlog and drive replica count without relying on HTTP request concurrency. The remaining options fail one or more requirements because B. Container apps supports custom non-HTTP scaling signals. C. Manual automation is unnecessary for the supported scaling rule. D. AKS is not required merely to use a service bus-driven scaler in container apps. Exam strategy. When container apps consumes messages rather than HTTP requests, configure a custom Kata rule for the event source. Question number 124. Tests careful elimination. Background. AdventureWorks hosts a GPU-backed model as an HTTP-enabled Azure container app. Current environment. The app uses multiple revision mode and retains non-zero baseline capacity to reduce GPU cold start latency. Business requirements. A new model version must receive only a small fraction of production requests during validation. Technical requirements. The canary mechanism must not require disabling the app's auto-scaling configuration. Which statement is correct? Watch for distractors that are valid services but wrong for this scenario. Next, option A. Weighted revision traffic splitting can be used for the canary independently of the app's minimum replica scaling configuration. Next, option B. GPU-backed container revisions cannot receive percentage-based traffic. Next, option C. Canary validation requires auto-scaling to be disabled. Next, option D. Weighted revision traffic splitting is incompatible with any workload that keeps warm replicas. The correct choice is option A. Weighted revision traffic splitting can be used for the canary independently of the app's minimum replica scaling configuration. The key clue points here because traffic weights are ingress configuration across active revisions, while replica minimums and scaling rules control capacity for each revision. A container app can keep warm capacity and still route a small percentage of requests to a new revision. Check why each remaining option is not the best fit. B. GPU-backed container revisions are not inherently excluded from percentage-based ingress routing. C. Traffic splitting does not require auto-scaling to be disabled. D. Warm replicas do not make revision traffic weights incompatible. In container apps, revision traffic management and replica scaling are separate concerns. Configure each according to rollout and latency requirements. Now tackle question number 125. Next, we enter the topic of Cosmos Vector Index. Review the scenario. A prototype semantic retrieval container in Azure Cosmos DB for NoSQL uses a quantized flat vector index. Only 600 embeddings have been inserted so far. What should the developer expect when vector similarity queries run at this small data volume? The choices are: option A. The vector query fails until at least 1,000 embeddings exist. Option B. Cosmos DB performs a full scan until at least 1,000 vectors are indexed, which can consume more RUs than the quantized index would at scale. Option C. Cosmos DB silently converts the query to keyword search. Option D. The quantized index operates identically regardless of the number of indexed vectors. The required response is option B. Cosmos DB performs a full scan until at least 1,000 vectors are indexed, which can consume more RUs than the quantized index would at scale. Here is the reasoning that confirms the answer. Cosmos DB requires at least 1,000 indexed vectors before quantized flat or discn is used. Below that threshold, vector queries fall back to a full scan, which can increase RU consumption. The incorrect choices are plausible, but unsuitable because A. Queries can run below 1,000 vectors. C. Vector queries do not become keyword searches. D. The documented small corpus behavior differs because the quantized index is not yet used. Use this elimination rule in the exam. For Cosmos Vector Search, expect quantized flat and discn to use a full scan until at least 1,000 vectors are indexed. Next is question number 126. Scenario. An Azure AI search index contains many millions of vectorized product descriptions. The vector profile uses exhaustive KNN, and latency grows sharply as the corpus expands. Which characteristic of the configured algorithm most directly explains the latency? Review the options. Choice A. Exhaustive KNN compares the query against the full vector space to find exact nearest neighbors. Choice B. Exhaustive KNN is an approximate graph search that becomes faster as the corpus grows. Choice C. Vector dimensions are ignored when exhaustive KNN is selected. Choice D. Semantic ranking forces every vector query to scan only text fields. The option that satisfies the complete requirement is option A. Exhaustive KNN compares the query against the full vector space to find exact nearest neighbors. Azure AI Search Exhaustive KNN is brute force exact search. It calculates distances across the vector space, so query work grows significantly with a very large corpus compared with approximate HNSW search. Here is how to rule out the alternatives. B. HNSW, not exhaustive KNN, is the approximate graph-based approach. C. Dimensionality is still part of vector configuration. D. Semantic ranking is a separate re-ranking stage and does not redefine exhaustive KNN as text-only processing. A useful exam pattern is this. Use exhaustive KNN for exact search when scale permits. Use HNSW when low latency at large vector scale is more important than exact recall. For question number 127, separate the requirement from the distractors. Identify the decisive constraint before considering the options. A developer enables semantic ranking in Azure AI Search and expects the semantic ranker itself to discover matching documents without first producing a search result set. What is wrong with this expectation? Eliminate every option that violates even one requirement. Consider option A. Semantic ranking is a second-stage re-ranker that operates on candidates produced by an initial text, vector, or hybrid query. Consider option B. Semantic ranking is a standalone replacement for first-pass retrieval. Consider option C. Semantic ranking can run only when vector search is disabled. Consider option D. Semantic ranking automatically creates an index when no query is supplied. The best answer is option A. Semantic ranking is a second-stage re-ranker that operates on candidates produced by an initial text, vector, or hybrid query. This option satisfies the complete requirement because semantic ranking re-ranks a bounded candidate set produced by first-stage retrieval. It improves ordering of existing matches rather than functioning as an independent document retrieval mechanism. B. The semantic ranker is not standalone first-pass retrieval. C. Semantic ranking can be used with vector or hybrid retrieval. D. It does not create indexes when a query is absent. Remember this decision rule. Think of semantic ranking as L2 re-ranking. Retrieve candidates first, then semantically reorder the eligible top results. For question number 128, separate the requirement from the distractors. The focus now shifts to AI Search Hybrid RRF. Pay attention to qualifiers such as least, most, and minimum. An Azure AI search request runs a full-text query and a vector query in parallel against the same index. Which mechanism combines the two independently ranked result lists into the hybrid result order before optional semantic re-ranking? Watch for distractors that are valid services, but wrong for this scenario. Next, option A, reciprocal rank fusion. Next, option B, alphabetical ordering by document key. Next, option C, a direct average of the raw BM25 score and raw vector similarity score. Next, option D. No merge occurs. One of the two query types is discarded. The required response is option A, reciprocal rank fusion. The decisive reason is Azure AI Search Hybrid Search runs text and vector retrieval in parallel and uses reciprocal rank fusion to merge their independent ranked lists into one unified ranking. Now eliminate the distractors. B. Document keys do not determine hybrid relevance. C. RRF works from rank positions rather than directly averaging incomparable raw BM25 and vector scores. D. Hybrid search combines both result sets. Watch for this clue in similar questions. In Azure AI Search, hybrid retrieval uses RRF to merge text and vector rankings before optional later-stage semantic ranking. Start by identifying the requirement in question number 129. Start by separating the facts from the requirement. A downstream processor reads the default latest version change feed from an Azure Cosmos DB for NoSQL container. The team expects a hard delete of an item to appear as a delete event in that feed. What behavior should the team account for? Use the scenario constraints to assess these choices. Choice A, latest version change feed captures creates and updates, but direct deletes are not emitted as delete events. Choice B, latest version change feed emits every delete together with all prior versions. Choice C, Delete visibility depends only on the account consistency level. Choice D. Change feed cannot be used for any workload that ever deletes an item. After elimination, select Option A. Latest version change feed captures creates and updates, but direct deletes are not emitted as delete events. The requirement to solution match is latest version mode exposes the latest create or update state for items. When an item is deleted, the delete itself is not captured as a change event in this mode. The remaining options fail one or more requirements because B. Delete records require all versions and deletes mode. C. Consistency level does not add delete events to latest version change feed. D. Change feed remains useful for create/update processing and can support delete-aware patterns through other modes or designs. Exam strategy. Latest version mode does not capture deletes. Use a soft delete pattern or all versions and deletes mode when delete events are required. Let's break down question number 130. The topic here is Cosmos change feed. First, locate the key operational constraint. An Azure Cosmos DB for NoSQL account uses continuous backup. A compliance processor must observe item creation, updates, explicit deletes, and expirations caused by TTL. Which change feed mode provides the required delete visibility? Review the options and eliminate any clear mismatch. Option A is latest version mode with strong consistency. Option B is all versions and deletes mode. Option C is latest version mode with additional provisioned RU/S. Option D is latest version mode with a longer default TTL. The correct choice is option B, all versions and deletes mode. The key clue points here because all versions and deletes mode records create, update, delete, and TTL expiration changes. It requires continuous backup and is the Cosmos DB change feed mode intended for true delete visibility. Check why each remaining option is not the best fit. A. Strong consistency does not add delete events to latest version mode. C. Additional RU/S affects capacity, not which operations are captured. D. TTL duration does not make latest version mode emit deletes. All versions and deletes mode requires continuous backup and is the mode to use when explicit deletes or TTL expirations must appear in change feed. Question number 131. Find the decisive clue before choosing. Look for the wording that eliminates the distractors. A Microsoft Foundry provision model deployment is sized for steady traffic. Spillover is not configured. Sustained demand pushes provision utilization to its available capacity. What should the application expect when the provision capacity is exhausted? Compare the options by fit, not by familiarity. Consider option A. Excess requests are automatically converted to standard pay-as-you-go traffic without configuration. Consider option B. Requests can receive throttling responses such as HTTP 429. Spillover must be configured if overflow should route to a standard deployment. Consider option C. The PTU allocation expands without an upper capacity boundary. Consider option D. The deployment shuts down until the next billing period. The option that satisfies the complete requirement is option B. Requests can receive throttling responses such as HTTP 429. Spillover must be configured if overflow should route to a standard deployment. Here is the reasoning that confirms the answer. Provision deployments have finite allocated capacity. When PTUs are fully utilized, requests can be throttled. Current Foundry spillover is an optional configuration that redirects eligible overflow to a standard deployment. The incorrect choices are plausible, but unsuitable because A. Standard deployment overflow is not automatic unless spillover is configured. C. Provision capacity is finite. D. Capacity saturation does not shut the deployment down for the billing period. Use this elimination rule in the exam. PTU gives predictable allocated capacity. Configure spillover separately when bursts should overflow to a standard deployment. Question number 132 is a good test of exam judgment. Focus on the requirement that drives the design choice. A team has provision throughput quota for supported Microsoft Foundry models in one Azure region. It wants to deploy a different supported model and is also considering moving the deployment to another region. Which statement best reflects the current PTU quota behavior? The exam distinction is hidden in these choices. Now examine choice A. PTU quota is model independent for supported models, but remains specific to a region and deployment type. Throughput delivered per PTU can vary by model. Now examine choice B. PTU quota is permanently bound to one model version and automatically transfers to any region. Now examine choice C. PTU quota is global across all regions in a subscription with no regional allocation. Now examine choice D. Every supported model produces identical throughput for the same number of PTUs. The required response is option A. PTU quota is model independent for supported models, but remains specific to a region and deployment type. Throughput delivered per PTU can vary by model. Current Foundry PTU quota is allocated by subscription, region, and deployment type and can be used across supported models. Model choice still affects minimum PTUs and the throughput delivered by a given PTU amount. Here is how to rule out the alternatives. B. PTU quota is no longer inherently bound to one model, and regional quota does not automatically transfer everywhere. C. Regional allocations still matter. D. Different models consume provision capacity differently. A useful exam pattern is this. Separate PTU quota from model throughput. Quota can be model independent, while region, deployment type, model minimums, and throughput characteristics still matter. Question number 133. We are moving to batch model processing. Scenario. A team must process a large archive of non-urgent summarization requests. Interactive latency is unnecessary, and completion within roughly a day is acceptable. Which Azure OpenAI capability is designed for this cost-sensitive asynchronous workload? Options. Option A. Global batch processing with its separate batch quota and 24-hour target turnaround. Option B. A real-time standard deployment with a requirement for sub-second responses. Option C. Provision throughput solely because batch processing does not exist. Option D. Increasing a synchronous rate limit while expecting the same batch pricing model. The best answer is option A. Global batch processing with its separate batch quota and 24-hour target turnaround. This option satisfies the complete requirement because Azure OpenAI Batch is intended for high-volume asynchronous processing. Global Batch uses separate in-queue token quota and targets completion within 24 hours at lower cost than Global Standard. B. Real-time standard deployment is optimized for synchronous requests rather than delayed batch economics. C. Batch processing is a supported capability. D. Raising synchronous limits does not turn standard traffic into batch pricing or execution. Remember this decision rule. Use batch for high-volume work that tolerates asynchronous completion. Keep latency-sensitive interactions on synchronous deployments. Focus on the key wording in question number 134. This scenario tests whether you recognize the controlling constraint. A customer support chat experience requires an immediate interactive response for each user message. A developer proposes sending each chat request through Azure OpenAI Batch to reduce cost. Why does the proposed design not meet the requirement? Focus on which option satisfies the complete requirement. Option A. Batch is asynchronous and targets delayed completion rather than interactive per-request latency. Option B. Batch provides lower latency than synchronous model endpoints. Option C. Batch supports only vector embeddings and never model responses. Option D. Batch requires every request to complete in less than 1 second. The correct choice is option A. Batch is asynchronous and targets delayed completion rather than interactive per-request latency. The decisive reason is Azure OpenAI Batch is designed for large asynchronous request sets with a 24-hour completion window target. It is therefore unsuitable for a chat interaction that requires immediate synchronous responses. Now eliminate the distractors. B. Batch is not intended to provide lower interactive latency. C. Batch supports more than embeddings, including supported chat completion workloads. D. The batch completion window is not a sub-second SLA. Watch for this clue in similar questions. Choose model deployment mode from latency requirements first. Batch is for deferred processing, not interactive request response traffic. Question number 135 contains an important exam distinction. This question moves us into Postgres QL vector search. The key exam clue is contained in this scenario. An Azure database for Postgres QL table stores document embeddings in a vector 1536 vector column. A new embedding model produces 3072 dimensional vectors, but the table definition is left unchanged. Why can the new vectors not simply be stored in the existing vector column? The exam distinction is hidden in these choices. Now examine choice A. A vector column has a fixed declared dimensionality, so 3072 dimensional values are incompatible with vector 1536. Now examine choice B. PostgreSQL automatically mixes different vector dimensions in one declared vector column. Now examine choice C. Different dimensions affect storage cost only and never the data type. Now examine choice D. Vector dimensionality is ignored whenever cosine distance is used. After elimination, select option A. A vector column has a fixed declared dimensionality, so 3072 dimensional values are incompatible with vector 1536. The requirement to solution match is a vector and column declares a fixed vector dimension. A value with a different dimension does not match that column definition, so the schema or stored representation must be changed before using the new embeddings. The remaining options fail one or more requirements because B. A declared vector 1536 column does not transparently mix arbitrary dimensions. C. Dimension mismatch is a type/schema issue, not merely storage cost. D. Distance metric choice does not remove dimensional compatibility requirements. Exam strategy. Treat embedding dimension as part of the vector schema. A model change that alters dimensions normally requires schema and re-embedding planning. Focus on the key wording in question number 136. This scenario tests whether you recognize the controlling constraint. An Azure AI search index stores embeddings plus structured fields such as tenant ID and document date. Vector queries must apply server-side filters on those metadata values. What must the index schema provide for those metadata fields? Focus on which option satisfies the complete requirement. Option A. The metadata fields must be configured with filter support, such as filterable, as appropriate for the field type. Option B. A vector field automatically makes every other index field filterable. Option C. Vector-enabled indexes cannot use structured filters. Option D. All documents must first be returned to the client and filtered locally. The option that satisfies the complete requirement is option A. The metadata fields must be configured with filter support, such as filterable, as appropriate for the field type. The key clue points here because Azure AI search vector queries can use OData filters, but the reference non-vector fields must support filtering in the index schema. A vector field does not automatically make metadata filterable. Check why each remaining option is not the best fit. B. Filter capability is defined per field. C. Vector queries can be filtered. D. Supported filters can be evaluated by the search service rather than only client-side. Plan metadata filters when defining the index schema. Vector search does not automatically index unrelated fields for filter operations. Move to question number 137. A legacy analytics solution uses Azure Cosmos DB Analytical Store to query operational data separately from the transactional store. A new item is written to the transactional store. What consistency expectation should the team have for the analytical copy? Option A. Autosync is asynchronous and analytical data can lag transactional writes for a short period. Option B. Every transactional write is synchronously visible in analytical store with zero delay. Option C. Each write requires a manual export job before analytical store can see it. Option D. Analytical store is the same row-oriented store as the transactional container. After elimination, select option A. Autosync is asynchronous and analytical data can lag transactional writes for a short period. Here is the reasoning that confirms the answer. Cosmos DB Analytical Store is a separate column store synchronized from the transactional store. Autosync is near real-time rather than synchronous, so recent operational changes can take time to appear. The incorrect choices are plausible, but unsuitable because B. Zero-lag synchronous visibility is not guaranteed. C. Autosync does not require an export for every write. D. Analytical store is distinct from the transactional row-oriented store. Use this elimination rule in the exam. A separate analytical copy can reduce operational RU impact, but near real-time synchronization still means some propagation latency. Work through question number 138. Step by step. Read the scenario with the target outcome in mind. A retailer uses Azure AI search and wants currently promoted catalog items to receive a business-defined relevance boost in addition to normal search relevance. Which index feature is designed to add this custom ranking influence? Check each option against the exact requirement. Choice A, a scoring profile with appropriate field weighting or scoring functions. Choice B, increasing Cosmos DB RU/S. Choice C, replacing HNSW with exhaustive KNN solely to promote one category. Choice D, disabling all ranking features. The required response is option A, a scoring profile with appropriate field weighting or scoring functions. Azure AI search scoring profiles add business-defined relevance influences through field weights and scoring functions such as freshness, magnitude, range, or distance. Here is how to rule out the alternatives. B, database throughput does not define search result ranking. C, vector algorithm selection is not a direct business category boosting mechanism. D, disabling ranking removes rather than adds the desired influence. A useful exam pattern is this. Use scoring profiles when business rules should boost otherwise relevant results. Use vector and semantic ranking for retrieval relevance rather than promotion logic alone. Question number 139. Take extra care here. One qualifier may decide the answer. Identify the requirement in this scenario. A team is validating several vector retrieval behaviors across Azure AI Search and Azure Cosmos DB. For each statement, select yes if the statement is true. Otherwise, select no. Statement 1. Test this claim. HNSW is approximate, so it can trade some exact nearest neighbor recall for faster search at scale. Statement 2. Test this claim. Azure AI Search semantic ranking can independently retrieve the initial document set without a text, vector, or hybrid first-stage query. Statement 3. Test this claim. Azure Cosmos DB quantized flat and disk-in indexes require at least 1,000 indexed vectors before the quantized index is used instead of a full scan. The correct judgment for Statement 1 is yes. HNSW is an approximate nearest neighbor algorithm designed to improve vector search performance at scale. The correct judgment for Statement 2 is no. Semantic ranking is a later-stage re-ranker and requires an initial candidate set. The correct judgment for Statement 3 is yes. Cosmos DB documents a 1,000 vector minimum before these vector indexes are used. Remember this decision rule. Separate first-stage retrieval from re-ranking. And remember that approximate vector indexes can have service-specific minimum data requirements. Move to question number 140. Identify the requirement in this scenario. A Cosmos DB for NoSQL container stores a large raw transcript property that is returned by point reads, but is never used in filters, sorting, or query predicates. Write RU consumption should be reduced. Which indexing policy change best addresses the requirement? Compare the options. Choice A. Exclude the raw transcript path from the indexing policy while retaining the property in each item. Choice B. Increase the consistency level to strong. Choice C. Delete the property from every item. Choice D. Explicitly include every property in the index regardless of query use. The best answer is option A. Exclude the raw transcript path from the indexing policy while retaining the property in each item. This option satisfies the complete requirement because Cosmos DB indexing policy can exclude paths that are not used by queries. Avoiding unnecessary indexing reduces index maintenance work and can lower write RU consumption while point reads still return the stored property. B. Consistency does not remove index maintenance for the field. C. The application still needs the property for point reads. D. Indexing and used large paths adds avoidable write work. Watch for this clue in similar questions. Index the paths your queries need. Point reads do not require every return property to be indexed. Approach question number 141 by checking every constraint. Next, we enter the topic of search refresh latency. Identify the decisive constraint before considering the options. A retrieval solution connects an AI application to an indexed enterprise data source that is refreshed on a schedule. The source system receives updates every hour. What should the team expect about when a source update becomes available in retrieval results? Eliminate every option that violates even one requirement. Consider option A. Availability depends on the ingestion or index refresh process, so some propagation delay can occur. Consider option B. Every source update is guaranteed to appear in retrieval results with zero latency. Consider option C. Connected grounding data can never be refreshed after initial configuration. Consider option D. The model retrains automatically on every source system write. The correct choice is option A. Availability depends on the ingestion or index refresh process, so some propagation delay can occur. The decisive reason is retrieval reflects the state of the search index or connected retrieval store, not necessarily the instant state of the source system. Scheduled or event-driven ingestion introduces a refresh interval or processing delay. Now eliminate the distractors. B. Zero delay synchronization is not guaranteed for all connectors and indexes. C. Retrieval data can be refreshed. D. Updating a grounding source does not automatically retrain the model. Exam strategy. For our AG freshness, distinguish source system update time from index or retrieval store refresh time. Question number 142. Tests careful elimination. Pay attention to qualifiers such as least, most, and minimum. An Azure AI search index is expected to contain about 50 million embeddings. The service needs strong retrieval quality but cannot tolerate the latency of comparing every query vector with every indexed vector. Which algorithm is the better fit? Compare the options by fit, not by familiarity. Next, option A, HNSW, because it provides approximate nearest neighbor retrieval with a practical latency and recall trade-off at large scale. Next, option B, exhaustive KNN, because exact brute force search always has the lowest latency at large scale. Next, option C, disable vector search because indexed retrieval cannot operate at this scale. Next, option D, either algorithm because their computational behavior is identical. The correct choice is option A, HNSW, because it provides approximate nearest neighbor retrieval with a practical latency and recall trade-off at large scale. The requirement to solution match is HNSW avoids exhaustive comparison against the full vector space and is designed for fast approximate nearest neighbor search at scale, trading some exactness for substantially better query performance. The remaining options fail one or more requirements because B, exhaustive KNN performs brute force exact search and scales less favorably for very large indexes. C, large scale does not inherently require disabling vector search. D, the algorithms have different computational and recall characteristics. At large vector scale, HNSW is typically chosen for low latency ANN. Exhaustive KNN is useful when exact neighbors are required and the scan cost is acceptable. Question number 143. Tests careful elimination. This is a hard question, so test every option against every constraint. Look for the wording that eliminates the distractors. An Azure Cosmos DB for NoSQL container stores 384 dimensional embeddings and currently contains fewer than 1,000 vectors. The team wants exact vector results at this pilot scale instead of relying on quantization. Select the most defensible vector index type for the /embedding path. Complete every statement by matching the requirement to the option. Statement 1. Identify the clue in. Configure the vector index type as the blank. The candidates are 1. Quantize flat, or disk ANN. The clue in the first statement points to flat. The pilot uses only 384 dimensions within the flat index dimension limit, and the requirement prioritizes exact results at small scale. Use this elimination rule in the exam. Cosmos Flat supports exact search, but has a lower dimension limit. Quantized Flat and disk ANN support larger dimensions and require at least 1,000 index vectors. Question number 144. Find the decisive clue before choosing. Pay attention to qualifiers such as least, most, and minimum. A developer proposes storing millions of embedding arrays in generic object storage and calculating cosine similarity against every stored vector in application code for each query. What is the main scalability disadvantage compared with using a purpose-built vector index? Watch for distractors that are valid services, but wrong for this scenario. Consider option A. The application performs a brute force scan whose latency and compute work grow with the corpus instead of using an optimized vector index. Consider option B. JSON arrays cannot store numeric vectors. Consider option C. Cosine similarity can be calculated only by Azure AI Search. Consider option D. Brute force object scanning has the same scaling behavior as an indexed vector search. The option that satisfies the complete requirement is option A. The application performs a brute force scan whose latency and compute work grow with the corpus instead of using an optimized vector index. The key clue points here because computing similarity against every stored vector is exhaustive scanning. A purpose-built vector index reduces query work and is designed to provide much better latency and throughput as the corpus becomes large. Check why each remaining option is not the best fit. B. Object storage can store JSON numeric arrays. C. Cosine similarity can be computed by application code and multiple vector services. D. Indexed and brute force retrieval do not have identical scaling behavior. A useful exam pattern is this. Use vector indexes to avoid application-level full scans when semantic retrieval must scale beyond small corpora. Next is question number 145. Scenario. A Cosmos DB container uses autoscale provisioned throughput with Tmax set to 20,000 RU/s. The application is nearly idle for an entire billing hour. What is the minimum autoscale throughput level used as the billing floor for that hour? The choices are option A, 2,000 RU/s, which is 10% of Tmax. Option B, 0 RU/s whenever no requests are made. Option C, 20,000 RU/s regardless of utilization. Option D. Autoscale has no minimum billable throughput. After elimination, select option A, 2000 RU/s, which is 10% of Tmax. Here is the reasoning that confirms the answer. Cosmos DB Autoscale has a minimum scale level and minimum billable throughput of 0.1 Tmax. With a 20,000 RU/s maximum, the floor is 2,000 RU/s for the hour. The incorrect choices are plausible, but unsuitable because B. Provisioned autoscale does not reduce its billable RU floor to 0. C. Billing is not always fixed at Tmax. It depends on the highest scale level reached during the hour, subject to the floor. D. A documented minimum exists. Remember this decision rule. Cosmos autoscale ranges from 10% of Tmax to Tmax. The 10% level is also the minimum billable RU/s per hour. For question number 146, separate the requirement from the distractors. We are moving to our AG chunking strategy. Look for the wording that eliminates the distractors. A retrieval pipeline divides long technical manuals into fixed-size chunks with no overlap. Important definitions frequently begin near the end of one chunk and finish at the start of the next. What retrieval problem can this chunking strategy create? Watch for distractors that are valid services, but wrong for this scenario. Next, option A. A retrieved chunk can omit relevant context that was split across the boundary. Next, option B. Non-overlapping chunks guarantee complete context for every query. Next, option C. Chunking eliminates the need to generate embeddings. Next, option D. Fixed-size chunks guarantee perfect retrieval regardless of document structure. The required response is option A. A retrieved chunk can omit relevant context that was split across the boundary. Without overlap, a concept spanning two adjacent chunk boundaries can be divided so that neither individual chunk contains all the context needed by the query. Controlled overlap can preserve continuity across boundaries. Here is how to rule out the alternatives. B. Boundary splits can remove context from a retrieved chunk. C. Chunking does not replace embedding generation. D. Fixed size alone does not guarantee retrieval quality. Watch for this clue in similar questions. Use chunk boundaries and overlap deliberately. Too little overlap can fragment context, while excessive overlap increases index size and redundancy. Question number 147 is a good test of exam judgment. The key exam clue is contained in this scenario. A Cosmos DB change feed processor runs on several worker instances. The workers share the same processor identity and must dynamically divide change feed work without all processing the same partition ranges. Which component coordinates work ownership and checkpoint state across the processor instances? The exam distinction is hidden in these choices. Option A, the lease container. Option B, the account consistency level. Option C, a hard-coded partition assignment maintained separately in each worker. Option D, no coordination mechanism is used. The best answer is option A, the lease container. This option satisfies the complete requirement because the change feed processor uses the lease container to store progress and coordinate ownership of feed ranges across worker instances. Leases are dynamically distributed, so each range is owned by one processor instance at a time. B. Consistency level does not assign feed ranges to workers. C. The processor provides dynamic lease distribution instead of requiring static manual assignments. D. Coordination is a core role of the lease container. Exam strategy. In Cosmos Change Feed Processor, the monitored container holds business data and the lease container holds processor state and coordinates distributed workers. Now tackle question number 148. Review the scenario. A large retrieval corpus changes gradually each day, but the current maintenance job regenerates embeddings for every document and rebuilds all indexed content after each minor content update. Which maintenance approach is generally more efficient while the embedding model and vector representation remain unchanged? Review the options. Option A. Track new and modified documents and re-embed or re-index only those items. Option B. Re-embed the complete corpus after every minor content edit. Option C. Disable indexing permanently. Option D. Ignore all content changes until an annual rebuild. After elimination, select Option A. Track new and modified documents and re-embed or re-index only those items. The decisive reason is when the embedding model and vector schema have not changed. Incremental processing avoids regenerating unchanged embeddings and reduces compute, indexing time, and write activity. Now eliminate the distractors. B. Full corpus processing repeats expensive work for unchanged content. C. Disabling indexing breaks retrieval. D. Annual-only refresh ignores legitimate content changes. Use incremental indexing for content changes. Reserve full re-embedding for changes that invalidate the existing vector representation, such as a new embedding model. Approach question number 149 by checking every constraint. Background. Northwind is expanding a retrieval application from a small pilot to a large production corpus. Current environment. The pilot stores 500 embeddings in Azure Cosmos DB for NoSQL and uses a quantized flat vector index. Business requirements. The team wants to understand vector query behavior before production scale is reached. Technical requirements. The production design should account for the minimum vector count required before Cosmos DB uses the quantized index. What should the team expect during the 500 vector pilot? Compare the options by fit, not by familiarity. Next, Option A. Cosmos DB uses a full scan because fewer than 1,000 vectors are indexed. Next, Option B. Cosmos DB refuses all vector inserts until the count reaches 1,000. Next, Option C. Quantized indexing behaves identically at every vector count. Next, Option D. The threshold applies only to Azure AI search. The correct choice is Option A. Cosmos DB uses a full scan because fewer than 1,000 vectors are indexed. The requirement to solution match is Cosmos DB requires at least 1,000 indexed vectors before quantized flat or disk-in is used. At 500 vectors, the query falls back to a full scan. The remaining options fail one or more requirements because B. Vector documents can be inserted below the threshold. C. Small corpus behavior differs because the quantized index is not used yet. D. This threshold is documented for Cosmos DB vector indexes. Use this elimination rule in the exam. Pilot RU and latency measurements below 1,000 vectors might not represent the behavior of a Cosmos quantized vector index after production scale indexing. Now tackle question number 150. The focus now shifts to vector search at scale. Background. Northwind expects its production retrieval corpus to contain tens of millions of vectors. Current environment. The architecture team is comparing exact brute force nearest neighbor search with indexed approximate search. Business requirements. Interactive retrieval latency must remain practical at production scale. Technical requirements. A small loss of exact nearest neighbor recall is acceptable if it provides substantially better search performance. Which strategy best satisfies the requirement? Choice A. Use an approximate vector index, such as HNSW or disk-in as supported by the selected vector service. Choice B. Perform an exhaustive comparison against every vector for every request. Choice C. Disable vector retrieval and return documents in insertion order. Choice D. store vectors in object storage, and skin all of them in custom application code. The option that satisfies the complete requirement is option A. Use an approximate vector index, such as HNSW or diskNN, as supported by the selected vector service. The key clue points here because approximate vector indexes reduce the amount of work required to find nearest neighbors and are designed for low latency retrieval at large scale, accepting a controlled recall trade-off instead of scanning every vector. Check why each remaining option is not the best fit. B. Exhaustive search performs much more work at tens of millions of vectors. C. The requirement explicitly needs semantic vector retrieval. D. Custom object store scanning is another exhaustive approach without vector index optimization. A useful exam pattern is this. At large scale, approximate index search is normally the practical choice when latency matters more than guaranteed exact nearest neighbor recall. Question number 151. Tests careful elimination. Background. Northwind uses Azure Cosmos DB for NoSQL for document metadata. Current environment. The account has continuous backup enabled. Business requirements. Downstream processors must react to actual document deletions. Technical requirements. Both explicit deletes and TTL expirations must be visible in the change feed. Which configuration satisfies the requirement? Eliminate every option that violates even one requirement. Consider option A. Use all versions and deletes change feed mode. Consider option B. Use latest version mode because it includes every delete automatically. Consider option C. Increase the item TTL value. Consider option D. Increase provisioned RU/S without changing change feed mode. The required response is option A. Use all versions and deletes change feed mode. Here is the reasoning that confirms the answer. With continuous backup enabled, all versions and deletes mode captures explicit deletes and TTL expirations in addition to other item changes. The incorrect choices are plausible, but unsuitable because B. Latest version mode does not emit delete events. C. Changing TTL duration does not change the capture semantics of latest version mode. D. More throughput does not add delete records. Remember this decision rule. Delete-aware change feed processing requires all versions and deletes mode plus its continuous backup prerequisite. Question number 152 contains an important exam distinction. Background. Northwind uses Azure AI search for a large technical document retrieval system. Current environment. The index contains searchable text fields and vector embeddings. Business requirements. Retrieval should benefit from both lexical matches and semantic similarity. Technical requirements. The combined candidate set may be semantically re-ranked after first stage retrieval. Which retrieval configuration best satisfies the requirement? Focus on which option satisfies the complete requirement. Now examine choice A. Run a hybrid text plus vector query. Merge the first stage rankings with RRF and optionally apply semantic ranking. Now examine choice B. Use keyword search only. Now examine choice C. Use vector search only and prohibit text retrieval. Now examine choice D. Return documents in insertion order with ranking disabled. The best answer is option A. Run a hybrid text plus vector query. Merge the first stage rankings with RRF and optionally apply semantic ranking. Azure AI search hybrid queries execute text and vector retrieval together and use RRF to merge the result rankings. Semantic ranking can then re-rank the eligible merged candidate set. Here is how to rule out the alternatives. B. Keyword-only retrieval omits vector similarity. C. Vector-only retrieval omits lexical precision. D. Returning insertion order does not meet either relevance requirement. Watch for this clue in similar questions. Hybrid search combines complementary first-stage retrieval signals. RRF merges them, and semantic ranker can provide an additional L2 relevance stage. Focus on the key wording in question number 153. Focus on the requirement that drives the design choice. A .NET in-process durable functions orchestrator records the current time by calling datetime. Now, the orchestration later resumes after waiting for an external dependency, and its history is replayed. Why is this implementation unsafe, and what should the orchestrator use instead? The exam distinction is hidden in these choices. Now examine choice A, datetime. Now is replay safe, so no change is required. Now examine choice B. Time AP is such as datetime. now are non-deterministic during replay. Use the orchestration context current UTC date time. Now examine choice C. Durable orchestrators cannot use any date or time value. Now examine choice D. The restriction applies only inside activity functions. After elimination, select option B. Time AP is such as date time. Now are non-deterministic during replay. Use the orchestration context current UTC date time. This option satisfies the complete requirement because durable orchestrators reconstruct state by replaying history and must remain deterministic. Date time now can return a different value on each replay, whereas the orchestration context exposes a history-derived time that is stable at the same replay point. A. Direct system time changes across replays. C. Orchestrators can use replay-safe durable time APIs. D. Determinism constraints apply to orchestrator code, not ordinary activity code. Exam strategy. Inside durable orchestrators, replace non-deterministic system APIs with replay-safe context APIs. Let's analyze question number 154. This question moves us into durable GUID generation. Review the scenario and identify what must be achieved. A .NET Durable Functions orchestrator creates a correlation identifier by calling GUID.newGUID directly in orchestrator code. The orchestration can replay many times, which change makes GUID generation replay safe while keeping the operation in the orchestrator. Now compare the choices one requirement at a time. Option A is continue using GUID.newGUID because replay preserves its result automatically. Option B is generate the identifier by using the durable orchestration context replay-safe newGUID API. Option C is generate the GUID from date time. Now, ticks. Option D is disable orchestration replay. The correct choice is option B. Generate the identifier by using the durable orchestration context replay-safe newGUID API. The decisive reason is GUID.newGUID produces a different value when orchestrator code replays. Durable orchestration context APIs can generate deterministic replay-safe GUID values for orchestrator use. Now eliminate the distractors. A. Direct GUID.newGUID is non-deterministic. C. Deriving a GUID from current system time is also non-deterministic. D. Replay is fundamental to durable orchestration reliability and is not something to disable for this purpose. Use the orchestration context GUID API when an orchestrator needs an identifier. Use normal random API is only outside deterministic orchestrator code. Question number 155 is a good test of exam judgment. This scenario tests whether you recognize the controlling constraint. A fan-out durable functions workflow invokes an activity for each document. The activity writes a processing record to a database. A worker can fail after an activity completes, but before its result is durably recorded. How should the database writing activity be designed? Focus on which option satisfies the complete requirement. Option A. Assume the activity can never execute more than once. Option B. Make the side effect idempotent, such as using an upsert or checking whether the processing record already exists. Option C. Remove all retry and recovery behavior. Option D. Move the database right into non-deterministic orchestrator code. The required response is option B. Make the side effect idempotent, such as using an upsert or checking whether the processing record already exists. The requirement to solution match is durable activity execution is at least once. If a failure occurs after activity completion but before the result is recorded, the activity can run again. Idempotent side effects prevent a repeated execution from creating duplicate or inconsistent data. The remaining options fail one or more requirements because A. Exactly once activity execution is not guaranteed. C. Removing recovery reduces reliability. D. Database input-output belongs in activity code, not deterministic orchestrator execution. Use this elimination rule in the exam. Design durable activities with external side effects for safe repetition because activities have at least once execution semantics. Question number 156. Find the decisive clue before choosing. The focus now shifts to provisioned throughput. Identify the decisive constraint before considering the options. A Microsoft Foundry provision model deployment is sized for normal demand. During an unexpected burst, the deployment reaches its allocated provisioned throughput. No spillover deployment is configured. What should the calling application expect when provision capacity is exhausted? Compare the options by fit, not by familiarity. Consider option A. Excess traffic automatically receives unlimited standard pay-as-you-go capacity. Consider option B. Requests can be throttled with responses such as HTTP 429 until capacity becomes available. Consider option C. Additional PTUs are created automatically at no charge. Consider option D. The deployment is disabled until the next billing period. The option that satisfies the complete requirement is option B. Requests can be throttled with responses such as HTTP 429 until capacity becomes available. The key clue points here because provision deployments have finite allocated throughput. When that capacity is fully utilized, requests can be throttled. Without configured spillover, excess requests are not automatically routed to standard capacity. Check why each remaining option is not the best fit. A. Automatic standard capacity overflow requires spillover configuration. C. The service does not grant free PTUs during a burst. D. Saturation causes throttling rather than a billing period shutdown. A useful exam pattern is this. Provision throughput is bounded capacity. Configure spillover if eligible overflow should route to standard deployment capacity. For question number 157, separate the requirement from the distractors. Look for the wording that eliminates the distractors. A team uses a provision model deployment for predictable baseline traffic and also has a compatible standard deployment in the same Microsoft Foundry resource. The team wants eligible requests that exceed provision capacity to overflow automatically. Which current capability should be configured? Watch for distractors that are valid services but wrong for this scenario. Next, option A, provision deployment spillover to the standard deployment. Next, option B, a DNS record that alternates randomly between deployment names. Next, option C, a permanent client secret shared by both deployments. Next, option D, no configuration is required because provision deployments always overflow automatically. The best answer is option A, provision deployment spillover to the standard deployment. Here is the reasoning that confirms the answer. Current Microsoft Foundry spillover can redirect eligible requests from a fully utilized provision deployment to a compatible standard deployment in the same resource. The incorrect choices are plausible, but unsuitable because B, DNS routing does not react to provisioned inference capacity responses. C, a shared credential does not implement traffic overflow. D, overflow is not automatic unless spillover is configured or applied for the request. Remember this decision rule. Use Foundry spillover for service-managed provision to standard overflow instead of implementing unnecessary custom fallback routing. Approach question number 158 by checking every constraint. Pay attention to qualifiers such as least, most, and minimum. A media company must summarize several million archived transcripts overnight. Results are not needed interactively, and completion within approximately 1 day is acceptable. What trade-off makes Azure OpenAI batch appropriate for this workload? Eliminate every option that violates even one requirement. Consider option A. It provides asynchronous high-volume processing at lower cost than comparable global standard processing in exchange for delayed turnaround. Consider option B. It guarantees sub-second interactive latency for every request. Consider option C. It eliminates the need to inspect failed batch items. Consider option D. It requires disabling content safety controls. The required response is option A. It provides asynchronous high-volume processing at lower cost than comparable global standard processing in exchange for delayed turnaround. Azure OpenAI Batch is designed for large asynchronous jobs with separate batch quota and a target turnaround of about 24 hours. The lower batch price is obtained by accepting non-interactive completion. Here is how to rule out the alternatives. B. Batch is not intended for sub-second interactive responses. C. Failed requests still require operational handling. D. Batch processing does not require disabling content safety controls. Watch for this clue in similar questions. Choose batch when throughput and cost matter more than synchronous latency. You have completed Set 4 of the AI-200 Microsoft Certified Azure AI Cloud Developer Associate Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please Please like this video, subscribe to Tech with Koushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.